Hello students, welcome back to my video lecture 6 on S block elements. So in my previous video I was talking about the chemical properties of S block elements. I have discussed two chemical properties. One is reaction solubility in liquid ammonia and the other one is with reaction with nitrogen, isn't it? Okay, under reaction with nitrogen I told you, among alkali metals only lithium reacts with nitrogen, other alkali metals do not react with nitrogen, whereas all alkaline earth metals reacts with nitrogen to form nitrides. Okay, what is the formula for lithium nitride? Li3n. And what is the formula for alkaline nitrides? It is M3N2, beryllium nitride Be3N2, Mg3N2, Ca3N2, Sr3N2 and barium Ba3N2. Okay, yes students, so let us continue now. Okay, see, I told you that when nitrides are hydrolyzed, they liberate ammonia gas with the formation of hydroxides, isn't it? I told you how to write the reaction, how to write this reaction, isn't it? So in lithium nitride we have lithium ion and nitride ion. In water we have H plus ion and OH minus ion. Okay, what did I tell you? You just have to cross multiply, correct? Okay, you just have to interchange the ions. Okay, interchange the ions, that's it. You have to interchange these ions, understood? Okay, and you apply crisscross method. See, I have lithium plus OH minus. Apply crisscross method. Okay, yes, plus one charge here and OH minus charge here. Okay, yes, we will get lithium hydroxide, isn't it? Yeah, lithium hydroxide and N3 minus and H plus. Crisscross method again apply. Okay, 3 to this side and 1 to this side. What is that you're going to get? N1, H3, isn't it? That is nothing but what? NH3. Yes, is this correct? Okay, no doubts, fine. And also about alkaline earth metals. About alkaline earth metals, look here, if I take beryllium nitride, what is the formula for beryllium nitride? Be3N2. Now hydrolyze this, again you're going to get beryllium hydroxide with the liberation of which gas? Ammonia gas. Whenever it might be any nitride upon hydrolysis will liberate ammonia gas. Okay, now how to write this reaction? How to write this reaction? How to remember this reaction in a simple way? So in beryllium nitride, which are the cations and anions? Beryllium ion B2 plus, nitride ion M3 minus, correct? Okay, and in water we have H plus and OH minus, correct? Again, interchange the ions, cation with anion and anion with cation. Okay, now so we have B2 plus and OH minus, and N3 minus and H plus. Guys, don't by heart the reaction, remember this way, don't by heart the reaction. Okay, apply crisscross method. Okay, yes, plus 2 charge to this side and OH minus charge to this side. Okay, 1 to this side and 2 to that side. What is that you're going to get? Yeah, we will get B1, OH2, correct? Okay, 1 to this side, 2 to this side. So we will get beryllium hydroxide, correct? Next, how about ammonia? Ammonia, okay, look here. No, 3 is multiplied here and 1 is multiplied here. Okay, as usual, we will get N1H3. That is nothing but NH3. Yeah, we got ammonia. Okay, so please remember this way. Don't by heart the reaction. Okay, clear? Yes. So that is about the reaction with nitrogen. Okay, they form nitrides. Okay, and also what is the point to be noted here? Okay, now sodium, potassium, rubidium, cesium, these alkali metals, they do not react with nitrogen, only lithium reacts with nitrogen. Okay, yeah, okay, fine. Now what is the next reaction? Okay, the next reaction is reaction with halogens. Reaction with halogens. Yeah, look at here, halogens. Okay, is this the fifth reaction? Yes, I suppose this is the fifth reaction. Reaction with halogens X2, where X might be equal to what? X might be chlorine, fluorine, bromine, iodine. Correct? Okay. Yes. Reaction with halogens. Understand this point? We have lithium, sodium, potassium, rubidium, cesium. Okay. Lithium, sodium, potassium, rubidium, cesium. And alkaline earth metals: beryllium, magnesium, calcium, strontium, barium. Okay, beryllium, magnesium, calcium, strontium and barium. Now see, all alkali metals, all alkaline earth metals, they react with what? Halogens. They react with all of them. Okay, all alkali metals, all the alkali metals. Okay, yes, all alkali metals, they react with halogens. Okay, and also all alkaline earth metals, all alkaline earth metals react with halogens. Okay, when alkali metals and alkaline earth metals react with halogens, okay, they form halides. They form what? Halides. They form halides. Okay. Okay, and look here, what is the nature, what is the formula for halides of alkali metals? Okay, alkali metals will form halides of the type MX, isn't it? Okay, MX, whereas alkaline earth metals will form halides of the type what? Okay, yes, MX2. MX2. Okay, correct. Alkali metals will form halides of the type MX, whereas alkaline earth metals will form halides of the type MX2. Very simple. Okay, very simple. For example, I'll take one particular example. What is it? What is this? Yes, let me consider. Okay, yes, reaction with chlorine. Let us consider the reaction with chlorine. Okay, yes, we know they form what? Lithium chloride. Okay, sodium chloride, then potassium chloride, okay, rubidium chloride, and then what? Cesium chloride. What is the formula? The formula is what? MX, isn't it? Okay, the formula is what? MX. Any doubts with this? They form lithium chloride, sodium chloride, potassium chloride, rubidium chloride, and what else? Cesium chloride. Cesium chloride. Any doubts? No doubts? Okay, yes. And how about alkaline earth metals? Look here. See, I cannot prepare beryllium fluoride and beryllium chloride. We cannot prepare beryllium fluoride and beryllium chloride by this method. No, I cannot prepare beryllium fluoride and beryllium chloride by this method. No, they can not. These two cannot be prepared. Cannot be prepared. Okay, by this method. By this method, they cannot be prepared by this method. Okay, then what else we have to do? Okay, only magnesium, calcium, strontium, barium, okay, they can form chlorides by this method. For example, magnesium reacts with chlorine, it forms what? Magnesium chloride. Okay, when calcium reacts with chlorine, it forms what? Calcium chloride. Strontium reacts with chlorine, it forms, okay, strontium chloride. Barium reacts with chlorine, it forms barium chloride. Barium chloride. But we cannot prepare beryllium fluoride and beryllium chloride by this method. Then what else we have to do? What else we are supposed to do to prepare beryllium fluoride and beryllium chloride? Okay, yes, what is that we are supposed to do is, see, in order to prepare beryllium fluoride, note this point, okay, in order to prepare beryllium fluoride, look at here, if I have to prepare beryllium fluoride, okay, what I have to do is, okay, I have to use ammonium, okay, NH4, yeah, twice BF4. This molecule is called as, okay, ammonium tetrafluoroberylate. What is this molecule called as? Ammonium, okay, tetrafluoroberylate. ammonium tetrafluoroberylate. See, when ammonium tetrafluoroberylate is decomposed, okay, when ammonium tetrafluoroberylate is decomposed, it gives ammonium fluoride plus beryllium fluoride, BeF2. Now we got beryllium fluoride. Look at here. Now we got beryllium fluoride. Are you getting my point? Okay. So when ammonium tetrafluoroberylate is decomposed, it gives beryllium fluoride. Okay, then how to prepare beryllium chloride? How do I prepare beryllium chloride? In order to prepare beryllium chloride, what I'm going to do is, okay, I will treat beryllium oxide with carbon, okay, with carbon and chlorine. Okay. Look here, when beryllium oxide is treated with coke and chlorine, it gives beryllium chloride and carbon monoxide. Okay, when beryllium oxide, okay, reacts with coke and chlorine, it gives beryllium chloride and carbon monoxide. Therefore, I cannot prepare beryllium chloride and beryllium fluoride and beryllium chloride directly by direct method. And understand one more thing, beryllium chloride, okay, it exists as a polymer, a dimer as well as a monomer. Okay, yes, beryllium chloride exists as a polymer, a dimer as well as what? A monomer. Okay, yes, what is that? See, in solid state, okay, in solid state, yes, note, all of them are important. See, in solid state, well, beryllium chloride exists as a polymer in solid state. It exists as what? A polymer, like this. It goes like this. Beryllium, okay, chloride, yes. Yes. One more chlorine if I take. It forms a bond with this. Okay. One more. Like this. Okay. Yes. Like that it goes. Okay. Like that it goes. It forms a polymer in which state? In solid state. In solid state. But in vapor phase, okay. Yes. Next point. In vapor phase, if the temperature is less than 1200 degrees centigrade, okay, in vapor phase, if the temperature is less than 1200 degrees centigrade, they exist as dimer. Again, in the same vapor phase, okay, if the temperature is greater than 1200 degrees centigrade, they exist in the form of what? Monomer. They exist in the form of monomer. Dimer means, how do you write a dimer? Just like this. Dimer, beryllium chloride. Okay, just this. Beryllium chloride. Look at this. Okay, yes. It exists as in the form of what? A dimer. Okay, when the temperature is less than 1200 degrees centigrade, in which phase? In vapor phase. Whereas if the temperature is greater than 1200 degrees centigrade, it exists in the form of a monomer. Okay, yeah, we shall take one more question. Let us understand a question now. Okay, observe this question. Understand this question carefully. Understand this question. Look at the question here. Okay, again the same question which I have taught you earlier in the previous video. What is it? Which is more covalent? Which is more covalent? Which is more covalent? Okay, I have lithium chloride, okay, yes, sodium chloride, then potassium chloride, rubidium chloride, okay, and cesium chloride, okay. Lithium chloride, sodium chloride, potassium chloride, rubidium chloride, and cesium chloride, okay. I told you, when the question is about covalent character or ionic character, so you are supposed to use which rule? Yes, you are supposed to use Fajan's rule, okay, Fajan's rule, isn't it? So what according to Fajan's rule? According to Fajan's rule, okay, yes, smaller the size of cation, smaller the size of cation, and larger the size of anion, and larger the size of anion, okay, more will be covalent character, isn't it? More will be covalent character. Say yes or no? More will be covalent character. Smaller the size of cation, larger the size of anion, more will be the covalent character. Which are the cations and which are the anions in these chlorides? We have lithium as the cation and chloride as the anion, okay. Sodium as the cation, chloride as the anion, okay. Potassium as the cation, chloride as anion. Rubidium as cation, chloride as anion. Cesium as cation and chloride as anion, isn't it? So in all these cases, the anion is same, okay. Chloride, okay. So we cannot judge the covalent character on the basis of chloride, because anion is the same in all the case, okay. But we have different cations: lithium ion, sodium ion, potassium ion, rubidium ion, cesium ion. I have told you, okay, as we go down the group, okay, yes, ionic size increases, isn't it? Okay, as we go down the group, ionic size increases. That means cesium ion is bigger than rubidium is bigger than, okay, potassium ion is bigger than sodium ion is bigger than lithium ion. In the sense, lithium is a smallest cation, isn't it? It is the smallest cation, okay, correct. So smallest cation with anion, okay, will be what? More covalent, isn't it? Okay, smallest cation with anion will form, okay, a covalent compound. More will be the covalent character. Therefore, what will be the order of the covalent character here? Okay, yes, lithium chloride is more covalent than sodium chloride. Sodium chloride is more covalent than potassium chloride, then rubidium chloride, then cesium chloride. Cesium chloride is least covalent, or it is more ionic. Are you getting my point? Lithium chloride is more covalent, less ionic, whereas cesium chloride is more ionic, less covalent, okay. Hope you have understood about reaction with halogens, guys, okay. Shall I move on to the next one? What is it? Reaction with, okay, formation of carbonates and bicarbonates. Formation of carbonates and bicarbonates. Yes. The next question, the next concept is, what is the next concept? The next is formation of carbonates. Formation of what? Carbonates. The next one is, okay, seventh reaction is formation of bicarbonates. Formation of bicarbonates. Are you getting it? Okay. Formation of carbonates and formation of bicarbonates. Well, look at here. How is carbonate formed and how is bicarbonate formed? Okay. See, we have alkali metals, isn't it? Such as lithium, sodium, okay, potassium, rubidium, cesium, correct? And okay, for example, the alkaline earth metals, beryllium, magnesium, calcium, strontium and barium, isn't it? See, all alkali metals will form carbonates of the type, okay, M2CO3, okay, whereas all alkaline earth metals will form carbonates of this type MCO3. Okay, for example, lithium carbonate Li2CO3, sodium carbonate Na2CO3, okay, potassium carbonate K2CO3, okay, rubidium carbonate Rb2CO3, okay, cesium carbonate CS2CO3, okay, beryllium carbonate BeCO3, magnesium carbonate, okay, MgCO3, okay, calcium carbonate CaCO3, strontium carbonate SrCO3 and barium carbonate BaCO3. So all alkali metals will form carbonates of the type M2CO3. All alkaline earth metals will form carbonates of the type, okay, MCO3. Now, when are these carbonates and okay, when are the carbonates of alkali metals and alkaline earth metals formed? When are they formed? When are they going to form? When, look here, when oxides, okay, and hydroxides, when the oxides and hydroxides of alkali metals and alkaline earth metals, when oxides and hydroxides of alkali metals and alkaline earth metals, when they react with carbon dioxide, when they react with what? Carbon dioxide, they form carbonates. They form what? Carbonates, that is either MCO3, okay, or M2CO3. Okay, alkali metals will form carbonates of the type M2CO3 and alkaline earth metals will form carbonates of the type MCO3. Any doubts with this? Okay, are you sure? Are you sure there is no doubt? Okay, any doubts? So again I am going to repeat, all alkali metals will form carbonates of the type M2CO3 and all alkaline earth metals will form carbonates of the type MCO3. When are these carbonates formed? When are they formed? When, okay, the oxides and hydroxides of alkali metals and alkaline earth metals reacts with carbonates, carbon dioxide, they form carbonates. They form what? Carbonates. Let us write the reaction. Okay, let us write the reaction. What is it? Okay, see the reaction. Now let us suppose that, okay, lithium oxide and lithium hydroxide. I hope you know the formula of lithium oxide and lithium hydroxide. Now when lithium oxide reacts with carbon dioxide and lithium hydroxide reacts with carbon dioxide, how to write the reaction? See, in the previous case I told you, whenever you are writing the reaction, I asked you to just interchange the ions, isn't it? Whenever you are writing the reaction, I asked you to interchange the ions. Here the ions are lithium. In this case, let me write it later. Okay. See, in this case, the ions are lithium ions and oxide ions. Lithium ion and oxide ion. But there are no, okay, no, carbon dioxide is not an ionic compound, it's a covalent compound. Carbon dioxide is a covalent compound, therefore there will be no ions. See, in this case, if you have a covalent compound in the reaction, note this point, if you have a covalent compound in a reaction, just dissolve that covalent compound in water. Just dissolve the covalent compound in water. When the covalent compound dissolves in water, what happens when carbon dioxide is dissolved in water? It forms what? Carbonic acid, H2CO3, isn't it? H2CO3. Now we have the ions. Look here, which are the ions here? We have 2H plus ion and carbonate ion, correct? Now we got the ions. Again I repeat, so whenever you are writing the reaction and if you want to write the products, just interchange the ions, isn't it? Now, okay, in lithium oxide we have lithium ion and oxide ion, isn't it? Okay, whereas in carbon dioxide is purely covalent, therefore there will be no ions. So when such covalent compound is there in the reaction, what you have to do, you have to dissolve that covalent compound in water. Okay, when carbon dioxide dissolves in water, it forms what? Carbonic acid. And what are the ions in carbonic acid? We have, okay, H plus ion and carbonate ion, isn't it? So now we have H plus ion and carbonate ion, CO3 2 minus. Now interchange the ions. Look here. So lithium, okay, lithium is going with carbonate, okay, crisscross method. Multiply 2 here and 1 here. So what is that you're going to get? Li2, okay, CO3 1. That is nothing but Li2CO3 lithium carbonate plus, okay, what else we have? We have, okay, yeah, H plus ion and O2 minus ion. H plus and O2 minus. Okay, what else? Come on, cross multiply. We will get H2O, crisscross method. So H2O. Don't worry about balancing the reaction now. Okay, because we have already learnt balancing the reaction in redox reactions. Is that correct? Hope you understood. Look here, when oxide of lithium is reacting with carbon dioxide, it forms what? Lithium carbonate. Correct? Any doubts? Okay, now what about the next one? Okay, what happens when lithium oxide? Okay, I told you, when oxides and hydroxides of alkali metals and alkaline earth metals react with carbon dioxide, they form what? Carbonates, isn't it? Now let us treat lithium hydroxide with carbon dioxide. Okay, yes, again if you want to write the product, just interchange the ions, isn't it? In lithium hydroxide, which are the ions? We have lithium ions and hydroxyl ions. But again, carbon dioxide is a covalent compound. It does not have ions. So if you have a covalent ion, try to dissolve this in what? Dissolve this in water. When carbon dioxide is dissolved in water, it forms what? Carbonic acid. Now in carbonic acid, which are the ions? H plus ions and carbonate ions, isn't it? So we have H plus ion and we have carbonate ions. Again, interchange the reaction. Okay, so what are the products formed? Again we will get carbonate, lithium carbonate and water. Okay, no doubts with this? Okay, that's so nice. And understand the property of carbonates here. See, okay, well, look at here. Okay, the carbonates of all alkali metals, alkali and alkaline earth metals are highly stable. The carbonates of all alkali metals and alkaline earth metals are highly stable. That means they do not decompose easily upon heating. See, there is an exception here. Except okay, lithium carbonate. Lithium carbonate is quite unstable. Lithium carbonate, okay, when it is heated, okay, under very small less temperature itself, it decomposes to give lithium oxide and carbon dioxide. Okay, whereas look at here, lithium carbonate is quite less stable. Okay, therefore at less temperature itself, it decomposes to give lithium oxide and carbon dioxide. Whereas the carbonates of other alkali metals and alkaline earth metals, they are highly stable. They do not decompose at ordinary conditions. Okay, only when okay, they are heated, okay, above 1000 degrees centigrade, okay, they decompose giving okay, oxides and carbon dioxide, oxides and carbon dioxide. For example, sodium carbonate, when it is heated above 1000 degrees centigrade, it decomposes to give what? Sodium oxide and carbon dioxide, not at less than 1000 degrees centigrade, okay, because carbonate of sodium, okay, is highly stable, okay. Okay students, we'll continue with the chemical properties in my next video also. Thank you.